Okay, thank you, Victor. Thank you for inviting me also here in Paris. Very nice always to be here. And I will talk about moisture recycling, so I try to go a little bit to a larger scale. But before that, I want to introduce you to this guy, John Dalton. He's one of my heroes because he really invented, let's say, the amount of water which is evaporated going to the atmosphere, forming clouds, and then, in a way, closing the hydrological loop. And if we are now in Paris, so Leonardo da Vinci also tried to make this hydrological cycle, but he didn't have this evaporation flux in his painting. So this is why he's one of my heroes. But he's also one of my heroes because of these apples. And do you know why I put these apples here? Does anyone know?
Daltonism.
Yeah, Daltonism. Eh? So he found out that people are colorblind. And I'm also colorblind, so I'm a hydrologist and I'm colorblind, so that's why he definitely is my hero. And for me, these apples in these columns are identical, and probably not for you, or at least, well, one of the 12 human men here also have this color blindness in there. Okay, so I want to go to the hydrological cycle, and this is a bit really where you can see the dynamics of this moisture recycling. So these are remote sensing data, and here it's only a few days where you can see the enormous amount of water which is evaporated from the Congo basin and the Amazon basin to the atmosphere and then raining out a few hundred kilometers away. And this goes, well, every time up and down, etc. So this is why, well, we are really interested in this phenomena of moisture recycling. And maybe this comes a little bit already to your question. So what we do know is that, so here on the top, on the down left corner, there we see the more or less the current evapotranspiration fluxes. So the amount of evaporation and transpiration from the forested system. And of course that coincides with the big, well, the more evapotranspiration you have, the more forest cover there is. But we also do know that we expect to have big land use changes till 2100. So, well, I think the challenge is what we do have is really to understand these impacts on the freshwater recycling, but also on the carbon and also on the biodiversity effects on that. But I will now mainly focus only on the freshwater recycling. So in a way what you can see is, so on the left-hand side you can see, well, this is more or less an undisturbed forest, and there you have these cycling of water, so the water evapotranspires to the atmosphere and then rain is coming back, etc. And what you can see is here is that the runoff is quite low. So most of the water is really recycled locally, let's say. And if we have this disturbance of the forested system, so then we go to a low cover, meaning that this local recycling doesn't work anymore, so all the water from the rain is moving to the rivers as runoff and goes directly back to the ocean. So this is what we, well, can hypothesize, and that's probably also what happens. So in a simple way, how the system works is, so we have a flow from the ocean to the land, which is called an effective source of precipitation, forms precipitation on the land. This precipitation infiltrates in the soil and can be taken up by the vegetation. So and then the ET, so the evapotranspiration flux, goes back to the atmosphere, and forming what you can call a local source of precipitation. So you can try to find out and to put this all in kind of figures and in conceptual ways. But what we really do have is one of the problems is, so how can we scale, let's say, all these small scale processes from Yost to the, well, global circulation phenomena at a regional or continental scale. And that's a bit what we can show here. So we have a spatial scale and a temporal scale. So if you have the biomass adjustment, so biomass, well, let's say one tree is 10 meters or so, and there are really slow processes of carbon gain and carbon losses and so on. So this is really going very slow, 2 decades. And then we have all, let's say, the atmospheric processes, which, can start from meters. So this is the pattern water budget from Jost, let's say. So that's on a scale of a meter to 10 meters or so, to the atmospheric circulations, which is up to 1,000 kilometers. So this is a bit, the problem what we do have is how can we connect these spatial and temporal scales together? And in a way, we are very often interested in these positive feedback mechanisms. So the positive feedback mechanisms from the land to the atmosphere. And in a way you can say, there are 2 main positive feedbacks in there, and that's what we call the precipitation evapotranspiration feedback. So if we start here, so this is a picture by Axel Kleiden, by the way, from several years ago. But if we have a small increase in precipitation, so we increase the precipitation, that means that the growing season is a little bit longer, productivity is higher, there's an extent of the grassland savanna, more evapotranspiration, more atmospheric moisture content, and more precipitation. So this is really, all the pluses will form this positive feedback. And always also important to remember, so the positive feedback can go up and down, but also can go lower and lower. So that's always important in these positive feedbacks. It's an acceleration of the system and can move to the different sides. And we also have the radiation albedo feedback, but I will mainly talk about this precipitation evapotranspiration feedback today. So one of the questions what we do have is, can we try to track, let's say, this moisture coming out of one tree, evaporates, going to the atmosphere and falling somewhere else as precipitation? So can we do that? So can we derive the sink-source relations in there? And then also one of the key questions what we do have, can we also understand future changes in CO2 fertilization, nitrogen fertilization, but also big land use changes or reforestation plans, etc. And then the effect on these moisture recycling. And I'll try to get a simple way of how we can track these moisture with particles, let's say, in the moisture recycling. And so this is the source of moisture. So this is the land, there's just a bucket of water, let's say, at T is 0, and this can evaporate, going to the atmosphere, and then it can move by the transport by the wind. It moves to somewhere, so we do this in 3 dimensions, so depending on the wind speed, etc. And then a part of that can precipitate out to the land, let's say, so falls on the land, and the rest of this amount of water is transported further away and goes to the second time step, can also allocate something. So this, of course, depends on all kinds of parameterizations, etc. And then it moves further and further, etc. So this is a bit how we can track the moisture. And we just track this moisture in existing databases in weather models or in climate models, etc. It doesn't matter in a way, because we just can, we know how much water there is as precipitation in these models, so we just can track then, let's say, where it comes from. So just to see the sink and source relations in these kind of databases. Just to have an idea how this works, so these black dots are the sources, so these are 2 sources in a way, and then we just run the model for 1 month, and this is the wind direction in February for the Amazon, let's say. And there you can see, so if we are here at the east of the Amazon, then it moves mainly, to the southwest. And if we go more to the west of the Amazon, then it moves more to the southeast. So in a way, it is more or less the same as this wind direction field. So we do this in a 1/4 degree resolution, and that's how we have, let's say, tried to understand the role of the moisture recycling, or at least the transport of that. But of course, what we do need to know is how much water there is evapotranspired by the forest itself. So for that we use a global hydrological model. This is work done in, this one cannot move down, no. So it's done work by Mark Beekens and Rens van Beek. They developed a global hydrological model, and we have used that for the Amazon. And there you can see the annual amount of transpiration on the left-hand side and the annual amount of interception evaporation. So the interception evaporation is the water which comes on the leaves of the forest, but directly moves back to the atmosphere, directly evaporates back to the atmosphere. So it doesn't fall on the soil, it doesn't infiltrate, it's not taken up by the roots. So that's all transpiration is. Transpiration is root water uptake, and interception evaporation is just the amount of water on the leaves directly moving back to the atmosphere. So in a way that we have two sources of water. And this is more or less the dynamics, the seasonality of the climate in the Amazon. So on the top end we have the precipitation. So in, let's say, August, September, October we have the dry season, and then about, well, 100 millimeters of rain is still falling then per month. And what we do see is that the transpiration is getting quite big during the dry season. And so together with the transpiration, together with the interception flux, is higher than the rain during the dry season. So meaning that they use the buffer capacity of the soil to have enough water to transpire back to the atmosphere. So that's really an important phenomenon in the system. So the dry season, so there's not enough rain falling during the dry season to have enough water to evaporate and transpire back to the atmosphere. Yeah? So it uses the buffers. Clear? So this is what we did, and then we just run our moisture recycling model, and then just to have some ideas about this how this works. And what we do see is that around 50% of all the water is recycled at least one time, meaning that the rest of the water is recycled 2 or more times before it moves to the ocean. So on average, what we can say is that it takes, 500 kilometers for one drop, moves to the atmosphere, is transported further away, and then comes down 500 kilometers away, and then you can have this up to 7 times before it moves to the ocean. And and it can take 10 days, let's say on average 10 days, that this moisture stays in the atmosphere before it rains out again. So this is a bit the dynamics of the system, what you can try to understand then. Yeah? Is this clear? Okay. So then we move to the sources of the transpiration and the interception. So for instance, for this transpiration flux, so the amount of water taken up by the roots going back to the atmosphere, about 24% of the water which is transpired in the Amazon will remain in the Amazon, so will rain out again in the Amazon. And for the interception fluxes, there's even more. Yes?
That line of high colored dots is a valley between 2 chains of mountains, or it is the northeastern slopes of the Cordillera?
This. So you.
Over 1,000 millimeters.
So this is the Andes, so on the left and the west-hand side. So it moves to the Andes, and then you have all this cloud forest coming in, so that is extremely wet.
The eastern slope of the...
Yeah, exactly. Yeah. So that is, and this is really, so this, the wind pattern maybe, so the wind pattern is, most of the time goes from east to west and then to the southeast, let's say. But you also have a couple of months where it moves more to the north end. So then it hits still the Andes, but then it moves to the north. So this is a bit the seasonal, depending on the ITC set. Yeah. So in a way, what we can say is there's more water from the interception, which remains in the Amazon, compared to transpiration. And what you can also see that annual patterns are more or less the same. But then if you go to the wet season, so if it's very wet, etc., then this interception flux is of course enormous, let's say. So a loads of amount of water falls down and that evaporates back, etc. And then you have really this humid climate, this cloud forest, etc. You were there, apparently not in the dry season, I guess, or well, just after the dry season. So enormous amount of dynamics, etc. And this is so really this interception, so this lower two value is just much higher compared to the transpiration fluxes. But if we move to the dry season, then we really see that the transpiration fluxes become more important in the recycling compared to the interception fluxes. And the reason, of course, is that it's getting drier, so there's less rainwater coming on the leaf, so you also have less evaporation from the interception fluxes, but mainly it is transpiration, and this is mainly this transpiration due to the deep rooting systems of these trees. And there we really have a big difference between, let's say, this deep-rooted vegetation and this more shallow-rooted grass systems, savanna systems, or crops. Of course, what we do have, we have all these transitions to crop systems in the Amazon. And this is a paper by one of my PhD students in Hesse, and he tried to, well, find out, let's say, the differences between forested systems, savanna systems, and cropland systems in the Amazon on the evapotranspiration. So these are the numbers for the dry season, and here you can see that a forested system, well, transpires more than 4 millimeters a day, while a crop system only transpires 2 millimeters a day, let's say, well, 2.2 or so. So there's a huge difference in that, and well, the main reason is that during this dry season is this rooting depth. And this and also your groundwater depth. So this is really crucial in understanding, let's say, the effects of potentially land use changes on this moisture recycling. So what we try to do is we try to understand, let's say, the internal recycling per different regions in the Amazon. So these regions are also a bit based on biodiversity, estimates on tree diversity, etc. And then you really can see contrasting effects. So if we really, well, go to the east of the Amazon, then only 20% of the moisture which is evaporated to the atmosphere and rains out remains in this same area. So meaning that if you have your land use changes in the east, that doesn't have much impact on the whole moisture recycling of the whole system. But for instance, if you go to the southwest of the Amazon, then 70% of the moisture, which is evaporated and transpired by the system itself, falls back in the same region. So this should mean that, well, in a way, it remains themselves in this wet condition, right? So this is really important to think about it. So meaning that if we have these land use changes in the southwest of the Amazon, this will highly impact the whole region. Well, lucky enough, the arc of deforestation is here more in this 36% area, let's say. So this is the main places where we have this deforestation today, but still it is an important issue. So this is more or less, let's say, what we have derived based on the current status, the current climate of today, the current forest cover of today, etc. And now we want to, well, to say also something about all these future trends in global changes. So we have CO2 fertilization, we have nitrogen fertilization, we probably have on one hand, large land use changes to crop systems, but we also have maybe all these big changes of reforestation ideas in there. So many things will happen, and this will definitely impact our moisture recycling. So if we think about these future land use changes, and this on the right hand side we have a picture about from Staver and also Hirota had in the same issue. They had both an analysis on what we call this bistability system and what shifts from grassland to savanna to forest or the way back. And probably Vasilis will talk about this, or not? Well, anyhow. But what we do see is that in a way only one part of the Amazon is currently forest and is also unistable. So it is only one possible stability in there. And then we have a large part which is currently forest, but can easily shift to a savanna system. So it is in this bistable zone. So and if we then put our projections of this internal recycling, then we can see that a big part of this bistable forest, which is currently forest, can easily shift to a savanna state. At least, well, that's what we think. Meaning that small changes of land use changes can have larger impacts because it has a remote consequence on your moisture recycling, etc. So that can potentially shift it to another system. And then we also have this Amazon what we call the Amazon paradox. So in a way, we want to produce, well, more feed and food from the Amazon, so that's why we have these land use changes. Somewhere here in this arc of deforestation. But just south of the arc of the Amazon, we have huge amount of agricultural lands, which depends on the Amazon itself, which depends on the rain from the Amazon, which comes from the Amazon. So if we increase land use changes in the Amazon itself, it will also impact the agricultural sites at the south of the Amazon. And that is why we have this paradox. So you can maybe increase productivity locally, but it has a remote effect more to the south. So in a way, we almost have a kind of geopolitical issues in here. Eh? So from who is the moisture, in a way. Yeah? But so, well, at least I found it quite interesting. So this is one of the trends what we really need to find out, and we try to model this also on the moment. Another aspect is of course what we call the CO2 fertilization. So what we do know is that the CO2 concentration is increased from 280 to above 400 ppm. And so it is for the vegetation itself. This is a stomata. You all are biologists, have a bit background in biology? Yeah. Almost. So the stomata are very, very small things, very small cells, and they take up the CO2 and at the same time they lose the water. And that is why this is this loss of transpiration, let's say. But in a way this vegetation becomes lazy because the CO2 concentration is increased with 50%. So it's much more easy to get this CO2 inside you, so you can increase your photosynthesis, your cross primary productivity. So it's no need anymore to open your stomata the whole day, but in let's say at noon during lunchtime, you can close your stomata and then you have done enough for the day. So it will probably reduce your transpiration, or it can increase your primary productivity. Yeah? So this is a bit the debate what we do have. And if we look to tree ring data, so these are from Frank et al. These are long-term data of tree ring estimates. And from tree rings you can estimate the water use efficiency. And the water use efficiency is your, let's say, your carbon gain divided by your water loss. And what we do see is that they said, well, in all these areas, in the semi area, it's, well, a little bit low, but let's say in the temperate and the tropical ones, etc., we see an increase in water use efficiency. So the vegetation becomes more efficient for the water. We still don't know if it is an increase in cross-primary productivity or a decrease in evapotranspiration. So this is not what it says. It only says this ratio is increased with, let's say, 30 or 40% over the past 100 years. So this is quite big. Well, we think that at least one of the reasons of this increase in water use efficiency is that we really observe also, it's a kind of adaptation of the system, that the amount of stomata has decreased over the past 150 years due to the increase in CO2. So this is the same species, and so this is only a small fragment of a leaf here. And here you can see that there are loads of stomata still on the leaf, and then 150 years later, we only have a few ones in there. And this is not only one species, so we have shown that over loads of species, etc. This is all measured in Florida, by the way, so we went to these laboratories, these botanical museums and so on, and there we really could select, let's say, so you all have, in the US you all have these botanists, and they are great, because they really did, let's say, in 1877, they picked a leaf, put it there in such a famous museum, and they only write down the species and the date. And we were able to collect this small piece of leaves, we put it under the microscope and just counted the number of stomata. And then we did it in all, from, let's say, over the past 150 years, and then we see these trends in there. So one of the reasons why the water use efficiency is increased is apparently by an adaptation of the vegetation. So there's no need to have anymore these large number of stomata. And also if we put this into perspective, so if we try to understand this large increase in water use efficiency and compare that to the current IPCC models, then we can see, so let's say the red ones, the black ones are the tree-yearing data. Then over the past 20 to 30 years you have these eddy covariance data where you can also have a kind of estimate of increase of water use efficiency. And then you can see that, well, let's say our model is having a 40% increase in water use efficiency, and then in the average of all the Earth system models from the IPCC, we can see that there's only a small increase in water use efficiency. So we think that some important mechanisms are still missing there. And then what we also do know is, so this is maybe going back to your question then, so that we just observe, so these are observations from leaf area index from satellite images, and this is then the trend of increase in leaf area index. And this, although this is green and red, so I have difficulties in understanding it, but on average what we do see is that there's a greening of the world. And this greening of the world is depending on this CO2 fertilization, on this nitrogen fertilization, and also already on the reforestation. And well, the estimate is that all these three mechanisms are equally important around. So for instance, this reforestation in the southwest of Asia, this is definitely observed already with the remote sensing data. But in a way, in the arid system, in the more arid systems in Southwest Asia, the effect on the moisture recycling isn't that large as expected. So, well, we don't know exactly what happens there still. But at least the general trend is the world is getting greener. So this is, well, at least quite nice, we think. And then, of course, there are also people we think, okay, we can try to reforest the whole globe. So this was the work by Bastin and all. What was just before summer? They made this calculation of a potential global tree restoration. And well, of course, it is a bit controversial paper. Eh? So there were loads of comments in science, let's say, about it. That also the savanna systems, what we now have today, also have a kind of biodiversity in there. And if you have, if you shift it to a forested system, then you lose all this kind of biodiversity, etc. So there are all kind of comments in there, and also one of the comments was that they didn't include the moisture recycling in there. So they only planted, let's say, the trees, and they tried to see, okay, will they survive or not? But they didn't include the extra effect. So this was, one of the triggers that we wanted to see, okay, will this have an impact? So one of the things what we currently now try to understand is also, what is this potential of forested systems? So now we look to all the, let's say, tropical forests, so for the Amazon, for the Congo Basin, and from Indonesia, Southwest Asia, let's say. And these are more or less the trends of the IPCC, the CEB 6 results in precipitation increase. And in a way, this is already quite nice to see, is that what you can see is that the Amazon is getting drier, the Congo Basin is getting wetter, and Southwest Asia is also getting a little bit more wetter, but not that extreme, let's say. So these are more or less the trends what you can, derive from the CEB 6 archive. So what we now did was, we have planted all these continents with trees, let's say, and then see how this can affect and have this cascading effect, and that it tips from a savanna system to a forest system or the way back. So this was a bit our idea. So it was quite a bit of calculations, of course, because you need to add extra every time, let's say, a grid cell with extra forest cover and see what kind of effects it will have on the system. And here we can see some results on that, and then we can say, so we now have again this bistability range, so we have a minimal and a maximal amount of forest cover possible. And then if we have this potentially shifts due to the future climates, then what we can see is that a part of the Amazon is getting too dry to have to still have the forest, but the blue part is getting more forest due to the change in precipitation, if we incorporate this moisture recycling in there.
Sorry, CO2 fertilization effect isn't included.
No. So this is without a CO2 fertilization, and no, only with the new estimates of the precipitation in there. Yeah.
It's not a capital.
No. We just sample, let's say, in the CEB 6 data now. We try to understand this moisture recycling, and then we play around with the forest cover, how that impacts, let's say, the system. So this is what we do now. Yeah. So, to conclude, so what can we say is that for the current climate, so what we have done on low resolution, then, we can track, let's say, this moisture from the source to the sink, but also from the sink to the source. So we can understand, let's say, these connections. And on average, let's say, there's maybe a nice number to remember. It takes, 500 kilometers to transport in one cycle, let's say, and then for the whole South of America, it can take up 7 times of this cascading before one drop enters the ocean again. And one cycle takes up to 10 days or so in the atmosphere, so your residence time in the atmosphere. So these are the numbers of today. And then, of course, we have these big future trends expected, which is that we just see that the world is getting greener. So CO2 fertilization. We also have enormous plans of reforestation. So this will also dramatically influence the moisture recycling. We also see that from the CMIX-6 outputs that some parts, especially the Congo Basin, is really getting wetter, and then a part of the Amazon is really getting drier. We think that all these kind of phenomena can have impacts on the shifts from a savanna state to a forest state or the other way around. But we also need to be careful with this, because what we saw is that, so this is the last slide, that you all have now these NGOs who say, okay, plant a tree and it will get wetter. All these kind of ideas. So, and people really think now that, for instance, in Africa, if you plant locally trees, then also it will become wetter due to an increase of precipitation. So this will not be the case, because this increase, if there is an increase, this will happen 500 kilometers away. So it is really important to have a good message on this, that it is not that simple that if we plant now trees, that becomes wetter, etc. So this is really an important remark on this. But well, anyhow, we still like to do the research, and we still think that we do some nice work. So this is, part of this work is done by Arie Staal, who was a previous PhD student from me and Martin Scheffer. And also from Robert Tuinenburg, who had his postdoc here in Paris and now moved to Utrecht. And also from Hugo de Boer, also from Utrecht University. Okay, thank you.
Thank you very much,
Stefan, for also for bringing large-scale phenomenon into the play. Questions?
So you mentioned, thank you for the very nice talk. Does it work? Yeah, it does. Okay.
Yeah.
So you said the Earth is getting greener due to a lot of reasons, but you sort of, maybe I would think, forgot to mention also warming as a driver of greening. So here in the northern high latitudes, I would say that, you know,
that's true.
CO2 induced warming might also increase sort of greenness. That's one point.
Yeah, that's true. So they don't mention that, I think, in this paper. So this is not work by me, from for the Boreal region, you mean, that especially the Boreal region will become greener because of higher, warmer temperatures.
Yeah, and also growing season extension, and maybe also the tundra ecosystems will get greener.
No, that's definitely true, yeah.
Yeah, I guess they make a really big case about land use in this paper.
This is, so the point they want to make indeed is, for instance, so India and Southwest Asia is really the land use change which has impacted the greening of the system. Yeah, that's true. Yeah.
And then I have one question, if I may, regarding the precipitation on the Congo Basin. So you said the models say for future precip it will increase, but if we look into observations of the last decades, actually we see a very strong drying trend there, and I wonder why. So is it, do these models represent this drying trend? And
so,
I don't know.
So these are, let's say, well, it is depending on, of course, also your RCP scenario. But if we just take the RCP 8.5, so these are just the average data of these 6 CMIP 6 models, which are, well, just out in a way. And then we can see that there is, I think, so especially in the middle of the Congo Basin, there's definitely an increase in
Yeah.
precip, eh? Yeah. So and
Some
that,
are-
yeah, but you know, there are many things missing in these IPCC models, eh, right? So well, that's also an important warning.
Yeah.
So if you will really have evidence of a drying trend also in the Congo Basin, yeah.
Yeah, just
Yeah.
wonder because I looked into that and
Yeah.
somehow the models and the observations
Do not match
fit,
totally. Yeah.
and precip is, I guess, a process that needs very high resolution for
Yeah, yeah.
modeling.
Yeah.
So yeah, okay, thank
Yeah.
you very much.
No, that's
Martin?
Yeah, thanks, Stefan. We have been trying hard to kill the Amazon forest in our model.
I know
Deforestation,
that.
but always, it always comes back.
Yes.
Maybe we did it in the wrong way.
Yeah.
But nowadays you read that we are close to a tipping point. So with the land use or clearing of 40% or something like this, everything will be gone immediately.
to a savanna state, eh? Yeah.
If you do the deforestation, it will be
Yeah.
killed. It will not come back. I'm not sure. So what do you think from your studies? I mean,
So
can you kill the Amazon forest by, or is there a certain threshold?
No. So what we do see is that doesn't. So still, there's over 1 meter of precip coming from the ocean to the land. So that's the minimum one, which is in principle enough to grow forest. But it seems to be that these savanna systems are also there present now with up to 1,500 millimeters precip. So that is then the question, why are they there? Well, we also find forests with lower amounts. So this is really this bistability region. So maybe it is not that precip alone is influencing this biome shift, let's say. Or it depends on the history, etc. But so in principle, you are right that, let's say, 1,000 millimeters of rain will be enough to have a forest. Yeah.
Dieter?
Yeah.
Oh, you had this slide on that the models underestimate the water use efficiency.
Yeah.
Is that, I just wonder what that means. So they tend to maybe.
Yeah, what we think is that in the current Earth system models, let's say, then the CO2 fertilization is not very well represented in the system. That's what we think. So then.
So they would tend to underestimate biomass growth, perhaps, and such, and thus the greening. At least the one due to CO2.
Yeah, so they are a bit conservative in a way compared to at least the tree ring data, and we have derived this model from the tree ring data. So our model is more or less in a way. So this work what I did in Exeter together with Peter Cox, and in a way it is just a kind of interpolation of all the data which are currently present. Yeah. So yeah.
And it's only for the past, of course.
Yeah.
Wonder how the future development then might be.
And it could be that we are overestimating it a bit. That's definitely, well, that can be true. But I think that these the current IPCC models are a bit, well, or conservative, or doesn't have all the mechanism, especially for the greening of the system. Yeah.
Alex?
So, well, CO2 fertilization consists of two effects. So one is the water use efficiency effect, and the other one is, increasing CO2 directly influences rubisco, this enzyme in the leaves, and thereby you also have water biomass increase. And maybe water use efficiency, the effect might be underestimated in the models, but the other effect, so the direct effect on rubisco, that one might be overestimated. So in total, one cannot say that biomass accumulation is overestimated in Earth system models.
So I didn't totally look to the carbon budget, only from a water budget point of view. I was interested in this.
But that might be true. Okay.
Any other questions from auditorium? Yes, please.
A very local question, localized. It's on the leaf. You mentioned the stomata density, which is decreasing. And did you try to see how it decreases with time? I mean, and that it could be a sort of proxy of CO2 in the atmosphere.
Yeah, so originally this idea about counting the number of stomata and the density of stomata on the leaves were done in a paleoecological environment just to make estimates on the CO2 concentration. And let's say then we came together and then we thought, oh, wait a moment, we can also turn that around. So we can also see, because of the past 200 years, we know the CO2 concentration. And then we can do just the other way around. But traditionally, the paleoecologists always have done this inference way of thinking. So we have the stomata around, well, what is it, 10,000 years ago, 100,000 years ago, and there they try to estimate the CO2 concentration on that moment. Yeah. But what we now do see, so we also do experiments in our greenhouses, and we have low CO2 chambers and high CO2 chambers, and if you put an oak in there, then after 1 year they already have adapted the amount of stomata. So it's a really quick process. So it is within their phenotypic variability of the plant itself, who can decide every year, let's say, what they have. They can decide to make more or less stomata depending on the atmospheric conditions. So in a way they can adapt very easily, and the reason, because these species are that old, probably, yeah, so they just have that in their genetic variability inside.
Okay, thanks.
In there, yeah.
A quick question, hopefully this seems too good to be true, is what's the downside of the decrease in density of stomata? Is it wood growth, or is there a downside?
I'm not sure if there's a downside. So I think from the plant itself, making these stomata costs quite a bit of energy. So it is more, and it is of course, if you can choose as plants to make more leaves to get more carbon with less stomata, let's say, then it is more beneficial for the plant itself. Of course, what we do see is that leaves are getting thinner. So it is really more easy to invest in more leaf area index. So they become more fragile, etc. So they're all and they also try to invest more in above ground carbon than below ground carbon, because they need to have less roots, etc. There are all kinds of effects at the plant itself, and I think it's just a way of dealing with. It's kind of optimality idea, how they try to have the best about carbon cane and other limitations. Yeah. So I'm not sure if you need to talk about a downside of that. So it's just, I see it a kind of range where they can decide how they want to have their system working. And of course there needs to be a kind of resilience in the system, etc. And there they try to decide. To the fire? Yeah, I haven't thought about that. That's maybe an interesting one. Although what I've learned always from Jost is that the fire is more and also from Victor, that the fire is more in the grasses than in the trees itself. Yeah, so I don't know. Yeah, but it is definitely an interesting question. Yeah.
Benjamin?
Well, it's half a comment and then half a question. Going back to what Martin was asking about killing the Amazon and actually what you mentioned about the bistability. And if I remember correctly, there was something in the Hirota paper that you mentioned, the one about 2011, and that the bistability in the tropical area should be linked not just to the precipitation and of course to the disturbances in this fire forest regime, but also to the seasonality of the precipitation. and she showed that that was playing quite a big role. So then I would wonder, how would the seasonality affect the Amazon case, especially in the central part, or if you have looked at it?
Yeah, that's well, I don't have an answer now, but I think it's definitely an interesting observation. Yeah. So this the sensitivity in this dry season it's really it's very interesting to see what can happen, let's say, and so what we also try to understand is, let's say, with or without moisture recycling, how this dry season is shifting. Eh? So, and then what we do see is that it has an impact of 10 days or so, 10 days effect. So, because of course in the wet season there's enough water coming in the system, so that doesn't matter. But let's say really in this offset of this dry season, then let's say one extra rain event can just have a larger impact on, and that is about, well, what we see is this effect is about 10 days difference, this order, which is for soya, for soy productivity, it's quite important, because you also have dual cropping there in the system, and that just, well, moves just around, let's say, this dual cropping, but if you have an extent of the dry season, then it can have problems, and then you can only have single cropping still. So it can just be a balance thing in there, but yeah. Thanks. Okay, thank you. Yeah.
Any other questions? If not, then thank you very much again, Stefan.
Okay, thank you.